In this tutorial, we will create procedural roof inside Houdini. At the end of this tutorial, you should have a simple setup for generating roof from any kind of input geometry. So for me, as a demonstration, I have this roof that I created like that, and after this for each loop, if we have created our roof like this polygonal roof, you can see that it's actually is divided into tiles, into the rows, and you can see that every row overhangs each other like a roof should, like that. So, and for the controls of it, you do not have to follow exactly this kind of shape. Everything here is customizable. Once you have extracted a single polygon from each one of these block of geometry, you can go ahead and control how many rows you want for your geometry, how many rows of tiles you want. So there's a lot to it. So let's get to it. To start off this tutorial, go ahead and create your test geometry. What I did is just went ahead and Boolean some shapes, and I made sure that I have many different angles for the tool to handle, and to make sure that they look correct. So yeah, so you can use just a basic box, but I would actually advise to make something like this, where different angles are showcase how they are going to be created. So yeah. So let's start by putting a for each primitive node. So first of all, we can put down a normal inside here so that it doesn't look that weird in the viewport. Actually, we can, well, yeah, let's put down vertices like that. It doesn't really matter, but just for the viewport. And then in a for each, so I want to go ahead and create a for each primitive. And most important thing that you want to do is go ahead and orient every one of these primitives to the well, I choose for this tutorial to the positive x-axis. So this is the most important thing for us to have some sort of starting point for creation of the rule, because if you're starting to like dividing some of these primitives in the orientation that they are right now, that's just not going to work. So yeah, we have to make sure that we orient them correctly, do our operations, and then rotate it back. Put down another normal, and this time we want to go ahead and create a primitive normal. And if you go ahead in a viewport and take a look at it, you can see this normal for every one of these primitives are always going to be perpendicular to the actual surface of the primitive. So this is our starting point to know how can we start to orient this primitive. And now I want to go ahead and put down a detail wrangle. So detail wrangle, we're going to write a little bit of a code inside here that we're going to handle basically a rotation in 2 steps. And before I start writing some code, I actually want to go ahead and maybe snap this and explain what we actually want to do. So for this primitive, we know that our normal is always facing that way, and our reference grid is inside here, like that. So for this tool to work, I want to make sure that every primitive that goes into this loop is oriented. Well, for this one, I choose the X, Y, and Z. I chose the positive x-axis for me to make sure that, so in this loop I want to make sure that every one of these primitives points, its normal points to the positive z-axis. So this sounds pretty simple, but one thing that we have to keep in mind is the fact that this roof has to point, basically it has to be tiled downwards, and it cannot be rotated. Basically it cannot be like tiles can be like sideways or all that. The tiles also always should point downwards. So this basically provides a little bit of a challenge how to generate this option, this kind of a logic. And the easiest way for us to do it is just getting the normal of this primitive, and then I'm going to do this in one step. So first step is going to be getting a vector that is parallel to the y-axis. and this is basically what I want to rotate it, this primitive to. And then once we have this normal, basically once the primitive is going to be rotated to this one, when the normal is actually parallel, we can go ahead and then rotate it around the x-axis, which is going to then be very easily pointed to the positive x-axis. But now we have to deal with the rotation, the primitive to the make sure that it's parallel to the y-axis. And the way it's going to be worked out is like this. So let me just go ahead and do this. Let's start by writing getting the normal of the primitive vector norm. I can call it normal. Primitive 0 attribute name is going to be normal. Primitive number is going to be 0. So we should not need to normalize this primitive vector, because this normal always going to give normalized normals. Now for the vector that's going to be parallel to the y-axis, it's actually a pretty simple vector. I'm going to pull this look2 equals prim. Actually not prim, I want to set. So set function is when you want to use variables inside for the vectors. And I want to use base of these vectors. So I want to go ahead and point normal 0. Basically take the x-axis of this normal. So the y-axis is going to be 0 now. And then the normal of the z is going to be also the normal of that one. And if you go ahead and take a look at how it actually looks now, and we can set prim attrib. Name is going to be look2 prim 0. Value is going to be look2. Mode, we don't need that. Like that, and make sure that you actually go ahead and normalize it. So this is pretty important to make sure that all the vectors are normalized like that. But we have done something like so you can see, if you take a look at and start to write down the vector, you can see it's basically pointing parallel to our y-axis like that. And it's going to basically always be that. If you put down a transform inside here, put inside here, and start rotating your vector, you can see it's always going to point parallel to the y-axis, which is exactly what I want. So I have these two vectors, and thankfully there's a really nice function for us to go ahead and rotate, make a rotation matrix between normal and look2. So the matrices are way we can rotate objects inside Vex and in mathematics in general, I guess. So in Houdini you can basically just use either matrix or the vector 4, which is quaternions or something like that. So matrices are going to be a little bit easier to understand, and after my little bit of a testing out, it basically made no difference. So both the matrices are going to be what I'm going to do. So and to actually showcase it, what I want to do is create a matrix. I'm going to call this ident mtx. So I want to create a empty matrix. This is basically, if you think about it, the matrix is basically a matrix that rotates. There's no rotation on it, but it's basically a matrix that I can write a rotation data into. So this is an empty matrix, and I want to use there's a function called dihedral, so which is also going to create a matrix, which is going to be computing the rotation of the two vectors that we're going to give it, which is normal and look2. Let's call this rotation mtx dihedral, and it's asks for two vectors. So you want to orient from the normal to the look2, like that. And if you want to look, you want to take a look at how it actually works in steps, what you can do is go ahead and create another matrix. Let's call this slurp equals slurp. And it asks for the two matrices. So we can, as a zero matrix, we can give our zero matrix as a base, and want to rotate it to the rotation mtx. And the bias we can use a float channel bias like that. And for actually, we can go ahead and create this parameter, and nothing is going to happen because we actually want to go ahead and these matrix rotations, we want to go ahead and multiply it with the current point position. And for us not to do this in multiple wrangles, what I can do is go ahead and put down a for loop, basically n point for this geometry. I'd call this pt, and pt, and the code is want to get the vector of the current point position point. So that's going to be p for position, point number is going to be pt, and I want to compute the new position of the point, which is going to be vector new position, which is going to be position multiplied by my matrix. So you can basically multiply matrices with the point positions to get the actual to see how it actually basically affect the geometry. And now we have our new position. What we can do is set point attrib, and we want to set our new position, point number pt, and value new position. And with a little bit of a luck, we should have our rotation done. And if you take a look at it, so this is bias is 0. Basically, this is our identity matrix. So basically, no rotation. And the 1 is matrix rotation of the our rotation matrix of the dihedral, which is basically looking to this position. If you take a look at it, you can see this should make sure that our normal of the primitive, is going to be parallel to the y-axis, like that. You can see, like that. So basically, any of these geometry that we are putting into. So there's a couple of edge cases, but in most parts, you can see it's kind of like a dismantling entire thing. And if you notice, we have a couple of edge cases which we have to handle, which is primitives that are actually pointing directly to the y, positive and negative y direction. So these two primitives, if you take a look at it, so let's actually go ahead and stop at the top primitive like that. So you see this method is not working on it because of the because it has no offset on x and z axis. And if you see in our code, we are putting y as a 0. If you think about it, it's basically 0, 0, 0, and basically it's not going to rotate it anything. So we want to go ahead and handle this particular case, because if you, let's say, put down like a transform node before the actual wrangle node, and if you go ahead and rotate it, as soon as it's z-axis rotate a little bit even, you can see it's automatically is going to be went ahead and rotated to its basically nearest parallel point. So yeah, so this is where we actually want to go ahead and handle this case. And to do that, what we can do is check the length of the vector that we are actually looking to. If length of the look to equals, so basically 0, if this is not a valid look vector, which is in this case, which is basically length is 0, I want to basically, now I have to basically give it an arbitrary axis to look at. So, and for that, I'm just going to say, look at the x on the x-axis. So what you can do is override this look2 vector. Look2 equals, and you can just put it as a something like this. So this is going to be x-axis. It's going to override it, but only for these cases. And you can see, if you put, you can see both of these. You will notice that also the bottom also is going to be now rotated to its sides because of the basically it doesn't really matter because it was negative 1, but it still has basically length of it is still 0. So yeah, so this is the edge case we want to fix. So we have done that, and so to clean this up, we don't need this slurp. This was just for demonstration. So we can delete the slurp, and also we can go ahead and delete this parameter. And I want to, so instead of this slurp, I want to rotation matrix multiplied by rotation matrix. So this is basically slurp at t1, like that. So this is correct. And for us to be able to rotate all of this geometry back, we want to set the detail attribute of this. Basically, we want to stash this matrix as a detail attribute on this geometry. So put down a set detail attribute, so name. So Houdini uses xform as a attribute name for the stashing of the transformations. So since we're going to have at least 2 transformations, I'm going to call this xform 0, and the value is going to be our rotation matrix. So mode, we don't need that. Okay, so we should now set it up. If you go to the details, you can see all these crazy numbers, which is most of the time you just hope for the best when you multiply something, and something like this should be us able to stash it back together. And if actually you can go ahead and put down a wrangle node, you can actually go ahead and put the geometry back on together, which is very simple. Put down the matrix. Let's call this x for 0, which is a detail attribute. So this is going to be so 0, and it's x for 0. So this is our attribute name we created. And now all we have to do is we can run over the points v at p, multiply equals, and to put it back together, we do not want to rotate it again by the same amount. We want to invert the rotation. So this is where the very handy invert function goes. Xform 0, like that. And if I rotate this correctly, it should put it all together. You can see how cool is this? I think it's really cool, actually. We have dismantled our geometry. Okay, right. My bad. You can see we have basically dismantled it together. All of it, basically we have dismantled it and then put it together like that. So yeah. So now I want to go ahead and finish my transformation. Make sure that now the normal points to the positive x-axis. So let's do that. So, and for the second rotation, I'm going to go ahead and copy this because we have to just modify this a little bit. So open up the second copy. First of all, let's make sure that we're going to stash xform 1. I'll sometimes, well, pretty often forgot to do that and then think about why it doesn't work. And now the thing that we want to change. So first of all, so our normals right now are actually not correct. So it didn't update once we have rotated around here. So you can see the normals basically stay the same, even though we are pointing to the different direction. So put down another normal node and put down a primitive normal. So this should make sure that our normals are updated right now. So we want to still get the normals, and for the look direction, we want to look at the x-axis. So you can just use let's actually, well, and we want to make sure that we look at the x-axis. So it's going to be 0, like that. So we want to look at the x-axis. So the length of it, we want to modify that one because we're going to have to fix the different edge case. But for most of it, we can go ahead and we still need our identity matrix, and we want to still use dihedral, which is look2, and I think this should already work. So let's take a look at it. So how does this look? Okay, so you see our pieces are basically all of them are looking correctly, but there is one problem, and some of these pieces are actually flipped. And I think the biggest problem is with this window one, like this one. So if you take a look at outside of this one, you see that this is probably this piece, or this maybe, but you see that it's basically flipped around. So the flipping happened because of the another edge case which can happen, which means that let's actually take a look at how it looks. So you see, before our second transformation, it looks like this looks correct. This is a correct position, but you see that this second rotation has actually went ahead and flipped it around because it has to basically rotate. Well, it has to rotate. Well, if our normal like that, you see our normal inside here is so if it's -1 on the x, which is, let's take a look at it. So this is a -1. So right. I almost forgot. So you see, it's basically pointing to the opposite point of the x, and for the matrix, they really don't like that. So even if, let's say, I want to hit it, just like this first case, I put down transform, and I rotate it just by a little bit, our rotation, you can see, is going to look correct. So you can see, if it's basically directly opposite of the rotation that it has to make, basically if it's 180 degrees that it has to make, you can see it's basically can figure out which direction to rotate to, and it basically went ahead and flips it around. But if I change it brush by a little bit, you can see at some point there is this annoying thing that's basically going to flip it around. And since we want to make our roof and to make sure that it's always we're going to overlay our tiles and one over each other, we want to make sure that it always points upwards. So this is the edge case we want to fix. And the edge case for the fix is pretty simple. Basically, I want to check the normal of the, since I know I want to point it to the x-axis, and I know that for the positive x-axis, the opposite is going to be negative x-axis. So I want to check if the normal of so that's going to be index 0 for the x equals -1. I want to go ahead and create a new rotation matrix. So I do not want to use this rotation matrix because this is not going to give me the result I want. So this is going to be if and else statements. So the else is going to be my this one. So I still want to use a matrix. So I want to put this matrix outside the if, like that. This is going to be my empty matrix. So basically it's always going to be that. And this if and else is going to override either basically based on input. So for everything else it's going to be a dihedral, but if it's an opposite of it, we want to go ahead and use a rotate function, which is going to write to the identity matrix. So we want to give it our identity matrix. Actually, we want to call this maybe like let's call this actually a rotation matrix because we want to override it. Let's call this rotation matrix. So the amount of it and the axis. So I want to make sure I do know that I want to rotate it by 180 degrees on the y-axis. So it's pretty, so if you think about it, let me go ahead and, so we have this is our axis of rotation. If you think about it, we want to make sure that we rotate this inside here 180 degrees around the y-axis, like that. And this is where the rotate function is very handy. And amount of rotation, it has to be in radians, and we know that 2 pi is 360 degrees. So what we can do is just to use there's actually a special variable which is a pi, which is going to give us a pi amount, which is going in radians going to be 180 degrees, and the axis is going to be y-axis like that. And if we have done this correct, we should go ahead and rotate it. You see, it doesn't like another declaration of the matrix, because we have already declared it. We can go ahead and delete this matrix like that. You see, we have handled this use case also, and we want to go ahead and also just copy this. Also get the second one, x form 2, 1, x form, which we should, yeah, that's correctly set up, and want to go ahead and multiply. So how we can combine matrices is just multiplying them. So inside the invert, we can just go ahead and multiply x form 0 and 1 like that. And if you take a look at it, we should be correctly put back together. And if you take a look at this one, let's take a look at these. Let's not put them together. Let's take a look at it. So this should make sure that all of our primitives, you can see all of our geometry is pointing to the x-axis like that. And also we have ways to put it all together back. So this is the place where we want to go ahead and do our modifications. So I'm going to put down, so what I'm going to do is put down maybe like a subnetwork. So this is we're actually going to roof tile creation. Let's call like null node. Let's call these base roof in like that. But this is basically our empty canvas to actually go ahead and work with our roof tiles. So let's start doing that. I want to start by creating actual kind of wrapper around this geometry, because this geometry is not going to work for me to creating tiles and all of that stuff. So put down a grid, and this grid should be aligned to the positive x-axis like that. Let's take a look at it like that. So rows 2 and 2 like that. I put down a match size node, and we want to make sure that we go ahead and scale to fit, turn off uniform scale, and then we can just put all of them in the center. So basically this grid is going to wrap around the be the smallest one to wrap around the entire geometry tile like that. So that's good. And now I want to create my tiles. So I'm going to use poly split node, and because of this geometry is always going to be the same, I have a couple of things that I can actually go ahead and hard code for this node. So I want to use split locations. So this is edge loop. You can use edge loop, and if you go ahead and put down the one edge loop, you can see it's going to use it like that. And if you start to use a number of loops like that, you can start putting them inside here. So I want to make it a little bit more user friendly. So the split locations, you can actually go ahead and delete all of this after the call and everything inside here. So basically this is, I think, basically the edge numbers. So this is 0 and edge 3, basically the opposite edge or something like that. So, but it's always basically the same because of our geometry is the same. And once we have split locations, the chain location along the make cuts. So yeah, it's basically just a place where to put the edge loop edges on which to put them, which is going to be these two like that. And the number of loops, since our geometry can vary in size, I want to uniform scale for my tiles. So this is where the subgeometry is going to come in handy. So I want to get use ch. I'm going to call this tile height. And then if you're using one of my tools, you can go ahead and create the float parameter, which is going to control the tile height, and to make it relative to the basically make relative to the height of this entire every tile that you create, we can use a division of the bounding box. So you can use bounding box that's going to be -1. So I'm going to actually explain why we're using a -1. Well, yeah, so we could actually go ahead and use 0 because this is geometry. So we can actually let's use 0 for now. And then d y size. So this is going to give us our height of the bounding box. We want to divide it by the height. And if you can see, if our tile height is smaller, you can see we have more tiles like that. This should be making sure that whatever the geometry comes in, the tile size is going to be consistent. If you go ahead and let's say put something like here, you can see we have more tiles because we have we have higher geometry, but the relative spacing between them should remain more or less equal, like that. So that's good. We have done that. And now I want to go ahead and use a for each primitive loop. We're going to loop it again. So for every one of these tiles. And before you start looping it, make sure that you actually let's take a look at how it actually works. So you can see it starts with a 0 from this top, right? So this is one thing to note how it actually works because you want to offset our tiles. If it kind of depends. You have to make sure that you know at what times every time this is going to loop through. So you can see mine is going to start from the top to bottom, so that's going to be I'm going to keep that in mind. And actually, since I made my previous network bit from the bottom to top, actually I'm going to go put down the sort node to ensure my sorting order. So for the primitives, you could put down the sort by y-axis. So this is going to make sure that it always starts for each starts with a 0 to the 0 to the max primitives, like that. So it goes upwards like that. So inside here, anything what I'm going to do inside here, I'm going to do with the thought in mind that I actually want to compile this, because this is actually going to be quite intensive basically operations. I want to make sure that I compile for every one of these. So let's start by poly splitting again. Poly split again. And this is basically we can use edge loop, and in this time I want to split them like that. If you take a look at them, you can delete them like that, edge loop like that, and then the same thing. Actually go ahead and copy the poly split like that. Instead of the y size, we want to use d size. Well, we want to use z size because the length of it is going to be on the z-axis. So go ahead and paste it inside here. So it's going to be z size. Instead of tile height, I want to tile thickness. Like that. And then if you're using one of my tools, you can go ahead and create your parameter. So this is my tiles. So this is probably going to be a lot more tiles because you want to go ahead and offset them to create kind of like this classical roof look, like that. So our tiles are done. Let's start by sorting, because I want to basically create the two groups that I can offset, and I want to sort by z-axis. My points are going to be sorted by z-axis. If you take a look at it, you can see, so it's going to start by here. You can see that basically every 2 points is going to be one edge. So this is, and since this is a sorting, I can be sure that this is always going to be the case, and I can easily create my edge groups, knowing that this is going to be always the case of these point numbers. So this is why the sort is so useful. And one thing I already forgot is the thing that I want to make sure that this works with the compiling. So that means we cannot reference ourselves in any of these expressions. We have to actually go ahead and use spare input references. So what I do is I select this, basically create one of my toolkits, add spare input. So basically I want to reference the node upstream and reference that one as any of these in any of these expressions that actually uses the geometry referencing. So wherever you would use 0, you want to use for the spare parameters -1, because once it's compiled, it basically, I guess it can't reference itself. It has to reference some other geometry. So for the compiling to work, we have to make sure that we reference other nodes and not ourselves inside expressions. So yeah, so that's good, and let's move on. And to create the groups, what I can do is put down point wrangle. Let me open this up. So inside here, it's going to be pretty simple. What I want to do is if. Basically, I want to check every 4 points, because every 4 points is going to cover my group A and my group pair 1 and group pair 2. So if at pt num modulus of 4 equals 0, so basically if it divides cleanly without remainder with 4, so that means that we are basically either at the point 0, we can be either at the 0, and then we can think about as a 4, 8, and all of that. So what I want to do is set edge group. So this is going to be a edge groups. So edge pair 0. So for the PT, so let's say so we know that at the 0 we have a first point at PT num, and we know that for the edge pairs, the next one is going to be the pair of the next point. Because of our sorting, we know the so it's going to be 0, the next one is going to be 1. So at pt num plus 1, and the value is going to be 1 for the groups, like that. And then we can just repeat this. It's going, instead of h pair 0, it's going to be h pair 1, and here I want to add, instead of 1, 2 and 3, like that. So this is a very simple way for us to get the to create 2 edge groups, which is going to be that we can go ahead and offset. You can see it works really nicely. Like that, we have created our 2 offset groups, and now we can go ahead and offset them. Put down a transform node, and if you go ahead and select edge pair 1, like that, and offset it, you can see we are getting this very typical roof shape, like that. And yeah, so one thing I want to make sure that we can actually go ahead and offset the roof. So usually there's basically our tiles are going to be overlap each other. So right now they are not overlapping. So this is definitely something we want to implement. And for the offset, let's put down a point wrangle. So to overlap these primitives, we can just go ahead and take all of the bottom points, and we can move them down, so that it doesn't actually impact our group that we have set up before that. Let me open this up. So in here, so I'm going to float. Let's call this offset, or maybe overhang. let's call this overhang, I guess, CHF. So let's call this like that. And now I want to get the bottom point. So we know that it's a straight primitive. We can use it by a y-axis, basically by y position. Let's get the bounding box minimum vector. Min equals get bounding box. That's going to be min. So it's basically the bottom part of the bounding box, and the y-axis should point right to these. Basically, the y-axis of this vector should basically be the same point position, which is all of these points are, which is basically 1.8, all of that. So if, because there can be some rounding up or down because of the because of the precision that we are working with so much of a decimal parts, we can just use the absolute, which is going to make sure that it's always positive. V at p dot y subtract the bounding box min. Basically is smaller than 0.001, some small number. So basically, if it's very basically if it's very similar to that, this should be correct. So why is it doing that? Implicit float. Oh, right, max dot y, like that. We can go ahead and move the v at p plus equals our overhang, like that. And it should basically make sure that only our v that p dot y, we only want to so now we have to use a negative. We can actually I guess we can use negative values instead of adding, but negative. That means that this parameter is going to move it like that. So this is going to be our overhang, and we can now, it's a good place to actually put down a UV texture. To set up our UVs, put it to the face. It should look something like this. So our basic UVs are done. Another thing that I want to make sure that I do not overhang the last primitives of this one, because since we are going to Boolean the shape, it doesn't really going to affect the last part of it. So for this tool, you should probably put in geometry that is already that has been already overhang if you want for the roof, something like this, or you can work around with that. So yeah, so I'm going to make sure that I do not overhang the last primitives. And the only thing I have to do is put down a switch if before the texture. I want to overhang only if it's so basically I do not want to overhang. Basically, if it's not the first one, I want to overhang, and if it is, then not. Create a meta import node, and let's go ahead and reference this inside this switch node. And then you can use a detail, -1, iteration, and it's going to be 0 like that. And then equals, so we want to make sure that it's when it's not, so not equal 0 like that. So most of the time it's going to be that, but on the first one it's going to be not overhang, and the rest of them it will be. Let's actually take a look at it, how it looks. So you can see, go to your wrangle node, you can see we are overhanging them, so we don't want to go overboard, something like this, just to see that they are overlapping each other. So that's done. So let me actually go ahead and also transform also these. So you see we are getting pretty nice look for now. We can also bevel them. Let's actually go ahead and bevel them. So once we have transformed it, we can put down the bevel. Then we can bevel both of these edge pairs. Edge pair 1, copy, and edge pair 0 and 1. Something like this maybe. So it really depends on the look that you're going for. So obviously we do not have any thickness to our roof. So after the beveling, we can probably go ahead and extrude them. So I want to make really a small amount of extrusion, maybe something like this. Make sure that we also output back like that, but it's going to be a problem because of the because they all of them are basically the same thickness and there is no offset. So this is where our transformation offset is going to be come in handy. Put down the transform node, and this transform should reference our loop count, which is iteration from our meta import node. So create a adds pair input, and in here we know that we want to move on the x-axis, and basically the higher it is, the more of the offset we want. So this is why we want to make sure that our offset is the amount that we are extruding. So just copy the relative reference of this thing, it paste it inside this one like that. But right now all of the offset is going to be the same movement. So this is where we want to one extrude multiply by our loop, the current loop, because the higher it goes, the more offset we want. So go ahead and multiply by detail. Let's go -1 iteration, and that's going to be 0 for that. And now you can see we should now have a really nice offset for each one of them. So you can see at the 0 there's going to be no offset, but for every one of them the offset is going to be multiplied by the current loop of the it's basically going to precisely overlap each other. So this is a very nice look for the roof. So now that we have this big tile, I want to go ahead and actually boolean this shape out. So just get the original geometry like this. You can just drag out something like here, put down a poly extrude. So in this poly extrude you can do something like this. So you want to make sure that there is some thickness to it. It basically is closed geometry like that. Basically it should be more thicker than anything that you want to your roof to be. So 1.2 is going to be 0.2 is going to be work out just fine. Now I want to make sure that it's a match axis. I want to match this to this geometry. Actually, I want to make this as a cutting geometry, and this is the geometry that I want to cut. Well, actually, I want to know if this is a match axis. This is not Boolean. I want to make sure that these are going to be the center, something like this. So basically, they should the roof bounding box should basically be inside here. So this is our cutting geometry, something like this. And then you can put down a Boolean, connect the first geometry like here, like that, and the only thing that you want to do is either subtraction and to intersect like that. So this is our cut-off geometry. So this should work most of the time. So we want to put down maybe normals before the actual edge. Maybe something like this. So you want to make sure that Boolean doesn't make weird shapes. You want to make sure that you have normals before. So inside here you see I have no normals. After the putting some normals down, the Boolean should look any of these cut faces should look fine for the most part, like that. And you can now put down an output. So this is our output. So there's going to be some problems, but it's going it's going to the right place where I want to put it correctly set up. So this is my roof tile that I have got out. So this is my input, output is this. Now I want to rotate it back on. So I want to connect this one, and I do not have the X forms are still there, so they should work with. Okay, so they're still there. So if you go ahead and you can see it's going to cook because but let's take a look at it. So there's going to be a couple of problems. First of all, there's well, the normals look completely wrong because of these inversion. So what I could do is put a normal node. Maybe something like this. Okay, so there's a couple of problems. First of all, the gaps between the roofs are not consistent because of the offset we have introduced in our roof tile subnetwork. Because of this geometry, so this is a small piece. I should probably take something bigger, maybe. Let's do the single pass, the big one. So if you go inside here, after all the geometry like that, go to the front, you can see because of we offset our tiles, our geometry is no longer straight. And if it's basically rotated back in the same place, it introduces this kind of a uneven parts padding between tiles. So we want to definitely fix that. So, and to do that, let's take a look how we can do that. And the way that I'm going to straighten this out is pretty simple. What I'm going to do is create a two point groups, which is going to be bottom point and top point, like that. And what I'm going to do is going to go ahead and take the very basically the minimum axis, basically the very first X point position, like that. I'm just going to rotate it. I'm going to rotate it. So basically, the bottom first point is going to be like a pivot to me, and I'm going to rotate the point here to that position, like that. Basically, just move them to so that first point on top and bottom are equal at the same X position, and basically that's it. So first of all, I want to create these groups. So I'm going to put down the wrangle node. I want to run over the details. I want to create these groups. It's actually pretty simple. Let's create a vector. Let's get the bounding box of this geometry. Let's call this bounding box max equals get bounding box should be max geometry 0, and then we want to also the minimum min. So we have our bounding boxes, and now I want to get all the points that are within the bounding boxes of these two vectors. So it's going to be string. Let's call this top pts equals. This is going to be string, and this string is going to be just like you can write in a group to select certain points. You can use add p dot y. Let's say it equals, it's larger or equals to, and then we can plus, and then we can use this position of the max bounding box position as a cutoff area for cutoff point for our point. So, and to convert the float, which is these vectors, it's going to be a float element, we can use a sprintf. The format I always use just as a D, like that, and the format is going to be our bounding box max dot y, the y bounding box position, and actually going to subtract a little bit from it because of the precision. We maybe want to start getting these points a little earlier, so maybe something like that. So this should basically take all of the points that are above this threshold string that's going to be used for the expand point group. So if you're not familiar, it's going to be very easy. we're going to write this out. So let me copy this. Let's paste this aside and let's use this as a bottom PTs. The bottom PTs are going to be, instead of the bigger, we want smaller. Instead of the bounding box max, we want to bounding box min, y. Instead of subtracting, we want to plus. So basically, we want to start a little bit above this point. So that's why we are adding to this. These are our strings that we can now catch our points all. So int, let's call this, let's actually call this str as a string, because we want to top pts equals expand point group 0, and instead of giving an actual point group, we can give these strings to it. It's actually going to find them, and it's going to be an array because it returns all the points that are within this parameter, like that. And then you can just go ahead and bottom pts, and then we can point it to these points. So we have our expanded points, and all we have to do is just go ahead and loop through them. Top PTs, int top PT, array top PTs, and all I want to do is add it to the group. Set point group 0 name top PTs. The point number is going to be top PT. Value is going to be 1. Mode, we don't need that. And basically we have looped over all of them, and let's loop through the bottom PTs. So bottom PT instead of top bottom, and set it as a bottom. And this should be done, and let's take a look at it. So let's go to this, go to the point groups. So we have put them as a, and make sure you do not have these double quotes in your groups. So I found this was a problem, but after all of this, it should basically work. Your group should be on top of it, like that, and in the bottom, like that. So now we can get our min and max bounding boxes. So put down another wrangle node. Put down, go to the code. And inside here we can use our group that we just created. It's going to be a vector. Let's call this top bounding box. Get bounding box. So I want to get the min bounding boxes on both of these, because I want to the minimum value of x get for both of them. Get bounding box min, and you can see that there's actually ability to us to give it a primitive group. So this is where our groups are gonna go in. Top, and then just copy bottom bounding box. Bounding box, it should be bottom PTs, like that. So we have our bounding boxes, and I want to generate our position that we're going to rotate from and to. It's going to be vector top position is going to be set. We're going to use these bounding boxes. Top bounding box, we're going to use 0, and top bounding box 1. And for the x, y, and z, and since z doesn't really matter, we can put it at 0. So that's going to be top bounding box. So top bounding box here, top bounding box 1, and that's going to be 0, like that. And I'm going to explain why we are doing that. And for the top position, bottom position, it's going to be same, but with the bottom bounding box. Right, so why are we not using 0? Well, that's pretty easily because of the rotation doesn't really matter. Because our point is going to be at 0, our rotation pivot along the z-axis is going to be at the 0. because that doesn't really matter. Only thing that matters is that our point is always basically at the center of this geometry, and at the correct position of the at the very end, at the very minimum x-axis inside here. So that's why we're using the axis as a 0. And now we want to get the vector that's going to point from the minimum point position on the bottom to the maximum minimum x position on top group. So basically what I want to do is let me copy this. So from here I want to imagine this is the end of it. I want to just get the so vector that's going to just straight point to this endpoint. So you can see if our was more slanted, if it was more slanted, we would want to get this vector, basically this vector that points to this, to the minimum points to of top group, like that, because this is the amount that we want to rotate from the positive y-axis. So imagine this is our tiles points to here, and this is the correct way which should point upwards. So this is the difference that we want to rotate our tiles to. We want to rotate it back to positive y, basically where y is 1. So that's what we want to do. So go ahead and we can just go ahead and subtract these. We can just go ahead and top position. Let's call this roof offset is equals top position, bottom position, and then we want to normalize it. Normalize like that. So we have our normalized vector, and all I want to do is go ahead and rotate it. And one thing that I have to do before I actually go ahead and rotate it, I actually created point groups. So for the quick fix, I'm just going to group promote and promote them to the primitive groups because of the this get bounding box actually expects primitive groups. Promote them to primitives. So let's take a look. So this is too much. I want to include all geometries on the boundary. Something like this. So make sure that you only select the very edges and edges of that. So yeah. So now this should actually go ahead and correctly set up a vector. And to check it out, we just have to, let's print out the vector, how it looks. Roof offset. And if you're lucky, it should not be 0. You can see it's not 0, so that's good. And we can also we don't need to run through the points, we can just do it once. And now I want to check how similar this vector is to the vector that just points upwards on the y-axis. So this is where the dot product comes in. So float, let's call this underscore dot, which is going to be dot. So A is going to be our roof offset, and B is going to be just a vector that points upwards, like that. And let's print out dot. It should be very similar. So you can see it's 0.99. So basically this means that these vectors are very similar but not quite the same. So if this would be 1, that means the vector points the same direction. The dot product would be 1, and if it basically points 90 degrees, that would mean that it's not similar at all. This would be 0. So between these places, it's where the dot product lives. And to get how many degrees you want to rotate this roof, you have to use inverse cosine function. So I'm not really the one who will explain all of this, because I really not expert on it, but I just know that once we do this, it's going to give us rotation amount that we need to rotate this geometry by. So let's just do that and try it out. So I'm going to call it float. Let's call it difference. in radians. So it's going to return the radians of this. So it's actually, we have to, since we're going to use it basically a transform node to control our pivot, we can actually just go ahead and set the detail attribute already, which are going to reference inside transform node. So set detail attribute. Attribute name is going to be rotation offset. Then you want to give the value that we set to. So this is going to be, since the transform node works with the degrees, you want to use the degrees, and the radians is going to be our a cosine, our dot product, like that. And this should be it. So it doesn't like the so I doesn't like it. No, make function. So it's I said detail like that. And if you take a look at the detail attribute, you can see we are rotating it by a very small amount. So let's go ahead and do this. So put down a transform. So this is transform is good because we want to set up our pivot. And pivot we want to, since we want to compile all of this network, I'm going to go ahead and create a spare input for this transform. And in here, I want to translate my pivot. Pivot translate. So let's take a look at where it's pivot now. See, we can move it. So I want to make sure that it's at the bounding box. Actually, I probably can use one of my tools. So bounding box, I want to X max inside here, like that, and then I want to Y min inside here. It's going to be Y min, like here. And for the, let's take a look at the pivot. So how does it look like inside here? So you can see our pivot is basically aligned to the top of this one. And now if we go ahead and rotate it, let's reference our geometry attribute. So which is a rotation offset. So what you can do is in the rotation for the Z detail -1 rot offset, and this should be 0, like that. So we are now rotated, and if you take a look at it, we have rotated by a small amount. But if you take a look at the at these points basically should be selected all at once. We can see we have successfully transformed this roof, and this is where we want to after all of this, you want to go ahead and change the input for this. So for the match size and for the Boolean, you want to Boolean these shapes out. Then for the output, go upwards. And if you take a look at this at the end of it, our so this is before the compile, but this should make sure that our spacing is at least predictable. We can obviously also make it a little bit better also. We could introduce like an offset for all of these pieces, which I'm actually going to do a little bit later, but the base of it is that it's correctly has set up. Make sure that tiles are going inwards, outwards, basically to the from the bottom it's on top of them, so that the top ones are on top of the later ones. So this looks really nice. So yeah, so let's do some cleanup and some final thoughts, and then it's going to be the end of this tutorial. So let's start by making sure that all of our references to other geometry is with this pair parameters. So I just found that this poly split. Actually, we're going to compile this entire network. So make sure that you actually go ahead and also a reference for this poly split also inside here as a -1. So I think this is basically the only one that I missed. Just clean some of these networks up, because we're actually going to go ahead and compile this entire network. So if we have done this successfully, everything inside here should be able to compile on its own. So go up one level. You see it's going to cook now. And also there should be everything also set up here for the compiling. So since you're using a lot of detail wrangle nodes, all of these can be compiled. So put down a compile block, and you can just put it inside here. So escape, and right before the normal, put it inside here, and you can see it's going to start executing. And make sure that you are so it's going to start compiling. Make sure that you are threaded when compiled for this for each loop, and this should actually go a little faster now. So one thing to note that so for something like this, maybe it's not the biggest deal, but if you have a lot bigger geometry, so something like this, where I have lots of so basically I have lots of geometry that needs to be intersected, it's actually going to be a big help. So you can see this compile block goes a lot faster. You can see I'm already at 1,000 once you are compiling, and if you can check if you're actually doing it, if your CPU is actually at the 100% because of the working of the multi-threading workflow. You can see we are basically creating this roof on every polygon, and if I go ahead and let's actually turn off compiling on this one, and let me just escape and put it on a visibility flag. You can see the for each loop is way slower. You can see our CPU is not really doing it's only one single thread working. So yeah, so this is one way we can check if for each loop is actually compiled. So yeah, so let's enable this compiling, and let me do this one, and let's put this. You see it's a lot faster. So yeah, so this is for the compiling. This will conclude this tutorial. So there's a bunch of stuff we can still do, something like ridges, which I think is going to be another tutorial, and also different roofs. But basically anything that you want to do custom is inside this for each loop. So once you are getting your single piece, you can start dividing it, do your stuff with your whatever you want with your tiles. This is all the custom stuff that you can modify all you want, because after that we are combining it together anyways. Yeah, so that's that. Is there anything else I wanted to mention? So yeah, for the ridges, there's definitely something that we can improve and start making some ridges. So that's definitely something I'm actually going to look into making. And so what else? So we can actually create some offset for this geometry. So after we have created our roof tile, and since we know that it's on the x-axis, we can just let's do this single pass, and we can go ahead and put down a transform node, and we just want to move it on the x-axis. So if we want to get closer, we have to go a negative value. So say maybe something like 0.03. Let's try it out. So that's maybe a little too negative. Make sure that you are negative to make difference smaller, basically the gap smaller. And let's turn off the single pass. Let's take a look. now you can see basically we have completely eliminated the well, you can, I guess, go ahead and make it. What would happen if you won? Okay, maybe 2 then. Okay, so now we are even kind of overlapping each other, which is still fine, looks fine. And if we are making some like ridges, that's going to not look too bad. So yeah, this is for the offset of the roofs. So yeah, so that's it for this tutorial, and see you next time, and hope you learned something. Bye.